Hello everyone, we are Group 4 and for this experiment, we are going to explore the conductivity of electrolytes. What are electrolytes? You've probably heard about electrolytes in energy drinks and salts, but really, what are they? They are the types of solute that when dissolved in water, dissociates into cations and anions which move in opposite directions in solution and have the ability to conduct electricity. This idea was first proposed by Sabban in his 1884 dissertation for which he won the Nobel Prize in Chemistry 9 years later. He also proposed that chemical reactions in solution were reactions between ions. In this experiment, the objectives are to set up an improvised conductometer at home, to compare the conductivities of tap and distilled water, to investigate the effect of concentration of different household solutes to the conductivity of a solution, and to determine the effect of temperature to the conductivity of distilled water.
The materials that we need are a multimeter with probes, lead wire, some soldering wire should suffice, a 9-volt battery, some electrical tape, a plastic pen barrel, 3 pairs of alligator clips, and some paper cups. We used cupcake liners. To make the makeshift probe, simply take 2 pieces of equal lengths of the lead wire and space them equally around the pen barrel, making sure that the bottom end of the wires line up with the bottom end of the barrel. Secure the top of the wires to the pen barrel with some electrical tape, leaving some overhang to serve as attachment points for the alligator clips. This is what your probe should look like. To complete our improvised conductometer, attach the red probe of the multimeter to the port labeled V-omega-MA and the black probe to the port labeled COM. Connect the red probe to the 9-volt battery through alligator clips. Connect the other end of the battery to one of the wires in your makeshift probe. And finally, connect the second wire to the black probe of the multimeters using the last pair of alligator clips. For the first part of the experiment, we set our multimeter to the 20 mA setting. Take equal volumes of distilled and tap water and measure the current separately by dipping the probe into the water with the tip touching the bottom of the cup. To get the conductivity of each sample, we divide the current reading by the voltage of the setup, which is 9 volts.
Here's the result for the comparison of the conductivities of tap water and distilled water. Our experiment showed that tap water has higher conductivity than distilled water as shown in this table. Tap water contains dissolved salts, which is also the reason why it's called hard water that forms soap suds in our bathrooms. Most of these salts are calcium and magnesium salts, which are present as bicarbonates, chlorides, and sulfates. These salts are strong electrolytes, hence we expect that tap water would be a better conductor. Distilled water, on the other hand, underwent evaporation and condensation already. That means that the salts were left behind, and this makes distilled water a poor conductor.
For the second part of the experiment, we will need some salt, vinegar, and some muriatic acid. For the salt solutions, we separately dissolved 1/8, 2/8, and 3/8 teaspoons of salt and about 30 ml of distilled water. I am using a small container as a measuring cup to keep the water volumes constant throughout the experiment. The same procedure follows for the vinegar solutions. For the muriatic acid, use 1, 2, and 3 drops in 30 ml of water. Just a side note here that when dealing with muriatic acid, make sure that you are working in a well-ventilated area and take extra care to avoid skin contact with the acid. Wear a mask and use gloves if available. Unfortunately, I don't have any gloves at my disposal or any long-sleeve clothing to protect my skin for that matter, so I was very careful while doing this experiment. Please do as I say and not as I do.
Here are the measured currents and calculated conductivities for the household solutes in increasing concentrations. It can be seen that for the 3 solutes, which are salt, vinegar, and muriatic acid, the conductivity increases with an increase in concentration. However, for vinegar, the increase in conductivity is only by small intervals, unlike those for salt and muriatic acid, which had larger increase in conductivity. In general, the direct relationship between concentration and conductivity is brought about by the increase in the number of ions per unit volume. Higher electrolyte concentrations means that there are more charge-carrying ions, and hence higher conductivity. But as we have noted from our data, the conductivity for strong electrolytes such as table salt and muriatic or hydrochloric acid increases sharply with increasing concentration because these strong electrolytes dissociate completely in solution, whereas for weak electrolytes like vinegar, the conductivity increases much more gradually because the degree of dissociation varies. To delve more into the effect of identity of solutes to conductivity, let's have Pauline to explain that matter.
So here, there are three categories: strong electrolytes, weak electrolytes, and non-electrolytes. For strong electrolytes, these conduct electricity well because these types of solute completely ionize or dissociate into ions in water. And these ions are the ones that conduct the electricity. Examples of this are soluble ionic compounds and strong acids and strong bases. For weak electrolytes, on the other hand, they only partially ionize in water. That's why they don't conduct electricity as well as good as strong electrolytes. Examples of this are insoluble ionic compounds and weak acids and weak bases. For non-electrolytes, these are usually the compounds that are soluble in water but does not dissociate into ions. An example of that would be sugar molecules and alcohols. So here, vinegar is a weak electrolyte because vinegar contains acetic acid, which is a weak acid. Hydrofluoric acid is also an example of a weak acid, and ammonia also falls under this category, it is a weak base, and silver chloride is an example of an insoluble ionic compound. So here, under strong electrolytes, one could see hydrochloric acid, which is a strong acid, and then salt, which is a soluble ionic compound in water. Other examples would also be sulfuric acid, which is a strong acid, and potassium hydroxide, which is a strong base. And for non-electrolytes, one example would be sugar, sucrose or glucose, and alcohols like methanol and ethanol. From what we can see in the experiment, it conforms with the expected results, which is that salt, which is a strong electrolyte, would show higher conductivity than vinegar, which is a weak electrolyte. And also hydrochloric acid would show higher conductivities. You can see here that the conductivities of salt and muriatic acid, hydrochloric acid, are relatively close, while vinegar's conductivity is smaller than the two. And here's for blank, which is even smaller than the vinegar, the conductivity of the vinegar.
To study the effect of temperature, 3 samples of distilled water with different temperatures were prepared. Since I only had a digital thermometer at hand, we kept the temperature range narrow. We had a sample at room temperature, another that was heated in the microwave for 15 seconds, and for the last one, it was heated in the microwave for 45 seconds.
So regarding on the effect of temperature, the general rule for electrolytes is that as temperature rises, conductivity also rises. This follows the formula here, where lambda naught at a specific temperature is equal to lambda naught at 25 degrees Celsius multiplied by 1 plus beta times T minus 25. So from what you can see in the formula, the greater the difference of the temperature from 25 degrees Celsius, the greater this whole multiplier would be 1 plus beta something. And this is directly proportional to lambda naught, which is the equivalent conductance. So with a greater temperature rise, this would also increase the conductivity. For beta, for salts, it is usually 0.022 to 0.025, while for acids, it's in the range of 0.016 to 0.019. So this is the case for strong electrolytes. However, for weak electrolytes, this does not really follow this formula right here, because there are also other factors to consider, such as degree of ionization in weak electrolytes, which also varies with temperature. Now, here are the results from the previous experiment, and we used distilled water as the sample. Now, here are the varying temperatures of the distilled water samples: 32.8, 35.2, and 39.7. You can observe that they only slightly vary, but it's increasing. And we took the average of the 3 current readings, since from what you can notice here, the readings are quite fluctuating. So here are the average current readings in milliamperes, and these are the corresponding conductivities of the samples. As the temperature rises, you can see that conductivity also slightly decreases. This is opposite from what we expect, because we expect that as temperature rises, conductivity would also rise. The possible reason for this is that, the temperatures of the samples are not that far from each other, so we can't really determine or see that the resulting conductivities here is really decreasing as temperature rises, or they are just a product of fluctuations. And yes.
To summarize, higher concentrations of solute will conduct electricity better because more ions are present in solution. This is observed in the conductivity of tap and distilled water, where in tap water you'd see higher conductivity due to the high concentration of ions such as magnesium ions. The nature of the solute will also affect the conductivity of the solution, wherein strong electrolytes like salt and muriatic or hydrochloric acid will strongly conduct electricity, while weak electrolytes like vinegar or acetic acid are comparatively weaker conductors. Furthermore, conductivity should increase with temperature, but this relationship was not observed, possibly due to the temperatures being too close to each other. For recommendations, we recommend to use an alcohol thermometer, or at least a thermometer with a wider range than that of the typical digital thermometers in drugstores, so that the effects of temperature will be more apparent. Also, for the probe, maybe it uses sturdier wire than soldering wire, because the soldering wire was very easy to break between measurements due to the weight of the alligator clips clamped around the prongs. Here is our reference, and thank you for listening. Have a good day.